We're talking linear buckling. This is going to build off of last week's episode of normal modes because linear buckling is an eigenvalue buckling analysis. So we need eigenvalues, and that requires modal. So we're going to kind of, start from scratch once again. So for those that are following along at home, I'll just build my 12 by 5 little square. Today I'll put a hole in it. So I'll just go and make a little half-inch banana. I don't really particularly care about units or no units. So hit enter, trim that surface out. So now I can go and get rid of that surface in the middle. There's another little option now that allows you to trim that out. Just 1 or 2 less mouse clicks in order to get that. Once again, blue is just such a color. I mean, geez Louise. Oh, what is it? Thursday night football? I don't even know who's playing tonight. We'll pick this because it doesn't represent any team. All right, let me go ahead and mesh this. I'm not going to be particular about my mesh. Once again, that's fine with me. Okay, so so straightforward so far. So I'm just going to set this up so everyone following along at home can do this. I'm just going to use the model browser today. This is kind of how I set up small models, especially when I don't have to, do a lot of checking and don't have a lot of parts in my model. It's pretty easy to just set everything up for a pretty small model over here in the model browser on the left-hand side, via right-click create. So, in order to run, you go down your little checklist, you need a material. I don't spend too much time in units, as you all know. Just make sure that you're consistent with your units. These are the default units that HyperMesh has in it. What unit system is it? I don't know. It looks kind of crazy if you ask me, but it is what it is. So make my property card for the shell elements to essentially give them a thickness in the material that I just created. Thickness 0.05. Usually do 0.1, but since we're doing buckling, I actually do want this part to buckle. So I'll just give it a little thinner than what I normally do. And last thing well, not the last thing, but next step is we need to tell these elements that they are assigned this property, that they belong to this property. They have this, they're all 0.05, coconuts thick. Easiest way for me to do this, again, for simple models, you can just right-click on the property in the browser and assign it. It kind of takes you to the same button and workflow, but so it says that one property, and then you can pick whether you want components or elements. I usually just directly assign the elements and change my visualization so everything's nice and shaded. Okay, so that property is now, you can see via the color, put back on there. All right, so I got my component, my mesh, my material, my property. Probably need some loads and boundary conditions. So once again, these are going to be contained in a load collector. So unlike last week where we were doing modal, that didn't necessarily require like a forcing load or a forcing function in it. We could do a free, or we could just kind of do a clamped and see what happens if it's clamped. We do need some kind of loads and boundary conditions on this. So because in order to do buckling, right, we would hope that the part just doesn't buckle sitting still, but I suppose it could. But we need some single point constraints, or we need something to constrain it. We also need a load collector in order to apply a load. I'm just going to name these as such, and I'll come back and fill them in. You will recall last week we need a load step input for the eigenvalue analysis. So this EIGRL card. This is now contained in a load step input. Just rename it. And my method is I want positive modes. So I'm going to say we'll start at 0, but I don't know where to end. So I don't necessarily have a frequency range in which I'm interested in. I'm just saying, well, give me the first 10 modes, right? Because that's quick, it's easy. As they say, good enough for government work. We're going to go ahead and create a few load steps. I'm going to do the loads at the very end, by the way. And this is one of the nice things about OptiStruct. which is going to be the solver that we're going to run. Doesn't have to be, but that's what I have access to. So I'm going to do a few. So I'm going to do my linear static first. So let me just name this lin stat, where all I'm going to do is apply the SPC and the load that I'm about to create, these things that I'm about to create. And I just want to see what the displacement and the stress, kind of the normal engineering stuff is, right? This isn't a modal analysis. It's not buckling. It's just, static, linear static. Okay. I'll hit close. I'll right click, create another load step. This one I'm going to call free. So we did this last week, but kind of a quick review. If you'd like, this kind of drop down here doesn't do anything other than parse out the necessary info needed below. So this isn't, it's not important that you do this, but modal analysis, the method struct. If we do free, we don't need a constraint in it. We're just I'm going to apply the free, easy peasy. I'm going to make another one, load step. This will be our modal constrained. So once again, modal. This time I will pick the SPC. And then the method struct. Once again, you need your IRL card. And finally, to top it all off, what we actually came here for today is linear buckling, right? So lin buck. And this has linear buckling. What linear buckling adds to this whole equation is this idea that you kind of need some sort of preload. You need something to put the part in a stress state to see if it buckles, right? So that's kind of the addition here onto the modal analysis. So I need some sort of either linear static or other type of pretension or some sort of load case that loads the part initially, right? And this is what we're going to do with a linear static. We're going to kind of compress this part initially, and then we're going to see if it buckles. So we need linear static, and then we also need the IRL card. Okay. So those are kind of your answers for linear buckling, right? So the other things are, you can put them in if you need them, but not necessary. Okay. So I have my subcases, and they reference these load collectors. These load collectors just don't have anything in them at the moment, so I'm going to double click on them and kind of fill them. You need to make them current, right? That's what the bold indicates. So any kind of new load entity will get classified under this, we can call it a folder, I suppose, this collector. It's called a load collector. Collects loads. So my SPC is now current. I right-clicked and made it current. Boundary conditions, constraint. Just come and grab these nodes on the left-hand side, and I will just clamp them in all 6 degrees of freedom. Is this right, proper? We can argue over that, but this is an easy enough part. So next, I want to go ahead and load this plate. So I'm going to right-click and make my load current. And I will come to my loads button and pick just a single point load. Place it here. I would like this in the x-axis, as you can see. So I'll come in. This is in the panel. We haven't migrated the loads and boundary conditions yet, but I think we'll manage to answer these questions. So the magnitude, I'm saying a -100. Again, be good with your units. Don't follow my example. Know what your units are. But to me, this is just 100 elephants going to the left. Great. Okay. So pretty classic buckling, right? Just some kind of compression. Doesn't have to be compression. It can be any type of buckling. But this one's an easy demonstration. Okay. So just kind of looking through this, I have a material, I have a property, got some loads, boundary conditions, they're collected. I have some load cases, I have my IRL card. Everything should be good to go. So I'm going to go ahead and hit analyze and run OptiStruct real quick. This is just going to save to my documents. That's perfectly fine. Change this to analysis, even though I could leave it as optimization. It'll just run one iteration. I think this is good. So we'll hit OptiStruct, and I will run this, and then we'll do some post-processing, right? So when we do linear buckling, we're looking for essentially a value, an eigenvalue is going to correspond to a load factor, right? So this load factor above 1 means that this part can support this force times that load factor, right? So 100 if the load factor, well, let's just look at this kind of stuff. Like last time, I'm going to go ahead and split my screen so we can see all of the stuff at one time, because that's what we want to do. Close this down at the bottom. So I'll click over here on the top right to activate our post-processing. I will open the result file. I want to find it in my documents. Okay, this H3D file. Hit apply. Even though all of the analysis is contained in this one H3D file, I'm going to open it 3 separate times so we can see the results all side by side. Okay. So back to this top right one. All of my subcases are up here at the top left. So subcase 1 is subcase linear static. So if I'd like to just see the normal, displacement of this or the stress in this part, that's all going to be shown here. The bottom left, I will go ahead and change this to my modal constraint. Just a thick, flat plate, so nothing crazy. But the real question is the buckling, right? So that's in this bottom right-hand corner. So let me go ahead and change this to linear buckling. And we're going to start to see that all of these modes are quite small. So 0.0018. So keep in mind, these are load factors. So meaning that 0.0018, you can kind of take it this way. 0.0018 times this load, this force that we originally applied, is essentially what this could take without buckling, right? Anything over this factor will cause this part to buckle. Okay, so what we're really looking for is all of these numbers to be above, say, 1, right? So 1.1, good. 0.9, not good. Okay. I mean, unless you're on arrow and you're like really flying on the edge, then yeah, 0.9. Don't do 0.9. Okay. So we can just come down here. If you want to show the contours of the buckling mode, you can show that as well. But again, so that kind of begs the question, what do we do to change this? There's multiple things here. I think one of the easiest things in this model is to just bump up the thickness. So just to do that real quick, just to show you can be done, I'm going to go back to my top left, come back to my property. My property, all of the information is down here. So I'm going to change this to 0.1. And then I'm just going to run this again. I'll change the number here, 127, I guess. Again, this doesn't take but a second to run, and then I'll pull up these results so we can kind of compare and contrast. Obviously, this is a great step off for optimization, right? Like how, you just doubled that arbitrarily. Yes, I did just double that arbitrarily. And to be honest, it was a really darn lucky guess, I think, because I think our buckling modes are now above 1. So split my screen again into 6 times now. We're getting really splitty. Open this new H3D file. It was 127. 27. Why? And again, mostly interested in linear buckling. Right. So now we start to get modes above 1. Not all the modes are above 1, so certainly still some more work to do. But now you start to see some of these modes are above 1, especially when compared to the modes in our original. Okay. So that's kind of our intro to linear buckling. Lots of nuance and caveats to linear buckling. Lots of things can make this work and not work. Mesh quality, there's all sorts of things that shear locking and all sorts of things that come up just from a mathematical standpoint. But for a majority of use cases, this should be a pretty straightforward run and necessary, especially in Aero. Okay. So with that, next time we talk about some matrix browser, which is probably my most favorite tool in the entire Altair suite. Really, essentially, how can we use our CSV files within HyperWorks, or how do we get stuff out to CSV? Because for all being honest, 99% of engineering is just Excel at this point in our lives. So with that, I'm going to go ahead and stop the recording.